Good evening, everyone. My name is Kevin Lagore. I am the director of Focus Astronomy. Probably seen me before from the Skywatcher What's Up webcast as well. I'm the product specialist for Skywatcher. And welcome to the... sorry, it's been a while doing this. This is Starstream. Starstream is a virtual star party that takes place right here online. That's brought to you by Focus Astronomy, and we explore pretty much anything up in the nighttime sky without ever leaving home. We started doing this at the beginning of 2020, and quite frankly, it got burned out real quick, mainly because we were doing it every other week. There wasn't enough change in the nighttime sky to do that. So it's been a year. We've done a lot of upgrades, mainly thanks to all the efforts at the What's Up webcast, but we have a new computer, so it's a lot faster, a lot stronger. So we'll actually be able to have special guests on in the future, which will be really neat. Have a new mic system, so hopefully the audio sounds a bit better than the past. And of course, our telescope system has also been upgraded. We're using our remote system, which is actually hosted out at Skies Away Remote Observatory facility, which is in Central California. For a monthly fee, you can basically send your equipment out to Skies Away. They'll install it in their observatory. It's a border level 2 sky, which is phenomenal. And basically, you can remote into your equipment via the internet and control your telescope and take all kinds of cool pictures under perfectly dark skies, as long as it's clear, essentially. So if you've been following us on Instagram, seeing some of our images coming up, a lot of that is from this telescope system. So we're going to start doing this monthly. This is the first one, but this will be a monthly thing. That way there's enough time between the enough time between the episodes to where there's enough change in the sky. So these are about an hour and a half long, roughly. We can go to 2 hours. We're not really limited on anything, but anyway, so if you like what you see here tonight, please go ahead and subscribe to the channel, leave a like on one of the videos, and this will be a monthly thing, so just keep an eye on what's coming up. So this evening, I've got about a dozen targets picked out for us tonight, but before we get started in there, let me just bring up our live feed here. Okay, actually, I need to change screens. Boop, there we go. All right, so this is the Skies Away. Well, this is one of the observatories at Skies Away. Skies Away, like I said, is a remote telescope hosting facility out in Central California. That's where our telescope is hosted. This is the Falling Eagle Observatory, if you ever want to follow it on Instagram or Facebook or whatever. Our telescope that we're using tonight is the telescope on the northern part of the observatory that you can see there. That is a Skywatcher Esprit 150, so it's a 6-inch refractor. At the back of the telescope, collecting all the images and the data, is a ZWO 6200 monochrome camera. So it's a black and white camera that we generally, for astrophotography, like to use black and white cameras. They're a little bit more sensitive than their color counterparts, and it also allows us to use specialized filters to isolate certain wavelengths of light and study different things that we want to study up in the nighttime sky. So this is an extremely sensitive camera. The sensor is a full frame, so it means it's the same size as a piece of film. 61 megapixel sensor, so incredibly high resolution telescope system. And in front of the camera, I don't have a good shot of it right now because the telescope is actually aimed at something getting focused. In front of that camera is a filter wheel for our techie people in the audience that's watching. We're using an FLI centerline 10 position filter wheel, and that houses 8 filters inside of it. We have a luminance filter, which we'll be using tonight. That basically is a UV-IR cut filter, which is basically what we use to take the underlying structure of an image. So when you take a picture for astrophotography, you're going to start out with the luminance shot. That's basically all the structure and detail inside of your image is built on the luminance. And then we have a red, green, and blue filter in there, which isolates those particular wavelengths. And when you compile all that into processing software, you can make yourself an awesome color image. So those are 4 of the filters: luminance, red, green, and blue. We also have a couple specialty filters. We have a hydrogen alpha filter, which allows us to observe hydrogen being emitted by the wavelength of hydrogen being emitted by certain objects. We're going to use that a couple times the night. We have an oxygen 3 filter, which isolates double ionized oxygen. That's really common in emission nebulas and planetary nebulas. We probably won't be using too much of that this evening. And we have a sulfur 2 filter, another popular filter used in astrophotography. We're probably not going to be using that this evening. And of course, we have an IR pass filter, which allows us to look deep into some of the nebulas and cut through the dust. That one will not be used this evening either, but those are the filters that we have installed and regularly use on this telescope system. So this is our telescope, and this is at Falling Eagle Observatory, located at the Skies Away remote facility in Central California. We do have a bit of a bright moon up tonight, so let me bring up, this is Stellarium. Stellarium is a free software you can get online. It allows you to kind of show you what's up in the nighttime sky. We are in autumn, as many of you know. We're getting close to Thanksgiving here in the U.S., and with that, we still have some of our summertime objects up, but we do have some of the constellations basically still visible. A lot of the core of the Milky Way, that Sagittarius, Scorpio area, which is actually down here, that's set and gone for the year. The remainders right now, we still have Lyra the Harp, Cygnus the Swan, Aquila is kind of hanging in there. But that's kind of the final little bits of the summer season is setting. But we're going to be playing a little bit around in this area in Cygnus early this evening. And then you have some really interesting constellations like Cepheus and Cassiopeia. They have some really interesting, odd, dusty nebulas that are up in there that are quite a lot of fun to shoot. I don't know if we're going to get to those this evening because we're right past the first quarter moon. So it's a little bright out this evening out there. But we'll see, as things go, how they're going to look moving forward. Maybe in December we'll plan this along a little bit darker night to get the maximum capability. But we'll still get some pretty cool stuff tonight. Of course, we have Perseus. And up here we have Pegasus and Andromeda. We'll be hanging out in there for quite a bit this evening. And then we'll probably make our way down to Taurus afterwards, and we'll kind of be bouncing around the sky a little bit. I've got a lot of cool objects picked out tonight. Some of them are very easy. I'll tell you how you can find those in the nighttime sky and what kind of telescope it would take for you to actually see them. But, kind of a cool thing there. So, and let me get this out of the way. We don't need our webcam anymore either. I can make that disappear. Boop. And let's get started. So let me exit this. We're going to be in here a lot. So this software that we're using tonight is called SkyX. The mount that we have out at the observatory is made by a company called Software Bisque, one of the best mount companies in the world. And this is the control software for it. It's kind of a watered down version. It's called LTI. But it allows us to do live stacking. And in astrophotography, the way things generally work is we're trying to take pictures of very faint objects. And it doesn't make a lot of sense to have the shutter opened for a long period of time, like an hour. It's much easier with digital technology to take 5 12-minute images and then stacking them in software to combine to that 1 hour exposure, which that's what we're going to be doing tonight, kind of on a faster level. So let's get started with that. And the first target that I'm going to be doing tonight is called M27, or the Dumbbell Nebula. It's a very popular target during the summer months. So let's go ahead and type it in here. Hit find. And we're going to have the telescope. It's going to go off and slew it over to that target. M27, or Messier 27, is the 27th entry in Charles Messier's catalog, known as the Messier catalog. There's 110 objects in this catalog. Charles Messier was a French astronomer in the 1700s and observed and hunted comets. And as he was out there looking for comets, he was able to document all these other objects up there and came up with this catalog. And the Messier catalog is what that is. It's pretty much the intro level for deep sky observing and astrophotography. All 110 objects are fairly easy to do. They're great objects to observe, but we'll get into the details here. So we're going to pick our, well, let me get in the live stack. There we go. So let me just explain what's going on here real quick. We're going to be doing 30-second exposures, which means the camera shutter will be open for 30 seconds. If you actually take a picture with your phone or your camera and you hear it go click, very short exposure. Tonight, because we're shooting really faint objects, we're actually going to leave the shutter open longer. And the software over time is going to continue to take these pictures over and over and over again, compiling them to make them brighter and easier to see. So we're going to go ahead and hit start, and it's going to start that exposure. You'll see the exposure bar right here telling you how much time we have left on it. And it should look pretty interesting when it pops up. It's always kind of fun to see it. Let me pop that back up. I'm just moving some stuff around the monitors here. But there we go. So like I was saying before, M27 is the 27th entry in Charles Messier's catalog called the Messier catalog. There's 110 of these total. And the cool thing about these particular objects is they're fairly easy to see. And there we go. Actually got a little satellite right there too going across. But this is M27. M27 is a planetary nebula. Now, a planetary nebula is a star that was very similar to our sun, and as it aged, it started to shed off its outer layers into space, expanding as time goes on. Our sun will do the same thing in about 2.5 billion years or so. M27 is just one of those objects that is very easy to observe. So this is in the constellation of Vulpecca. And actually, I can actually pull this up for you guys real quick. Stellarium works pretty good for all this. All right. So M27 is actually located in the constellation of Vulpecca, which is this line right here. It's not far from Sagittaea, the arrow, and not far from Cygnus. So it's kind of between Altair and Vega up a little bit. So that is where M27 is located in the nighttime sky. You could take a telescope out right now and go observe that. But that is where M27 lies right there at a distance of about 1,360 light years from Earth. Let me pop this back up. So as the images continue to stack and come in, you'll notice the background's going to get darker. It's going to look smoother. The nebula is going to get brighter. We could actually stretch this a little bit. Stretching is a term you'll probably hear me use throughout this episode. Stretching basically just means you're pulling out more stuff from the data. It's kind of like processing, essentially. So, yeah, this is 30-second exposures, Mike. The ZWO camera that we're using tonight, it's a 6200. These are extremely sensitive chips. Like 90% light transmission on this. So, and we're running this at f7. So it's not the fastest telescope in the world out there, but it's very dark out there. The telescope and the camera are well matched to each other, but those Bortle 2 skies really help quite a bit. So this is the Dumbbell Nebula, or M27, 1,360 light years away, about 3.2 light years in diameter. You can see the little central star right in the center there. This was originally discovered by Charles Messier, like we were talking about before. It's the 27th entry in his catalog in 1764. Now, the term planetary nebula was not coined until 1784, about 20 years later, by William Herschel, who actually was the founder of Uranus. Now, the reason he called these planetary nebulas because they had a similarity to the look of Uranus. So that's where he coined the name for planetary nebulas. Mike, the telescope tonight is 1,050 millimeter focal length, and this is a full frame camera, 61 megapixels. We're actually binning it 2x2 right now, which increases the sensitivity. So we're only running at 16 megapixels Oh no, 16 megapixels, which it's still a lot. We can actually zoom in on this. So let me do a digital zoom here and blow this up a little bit. We can really get into the structure of this stuff with this. This telescope does a very, very nice job. You can see how sharp these images are. But yes, this is M27. This object is very easy to see in most amateur telescopes. From a backyard, a simple 4 to 6 inch telescope or bigger, especially when there's no moon in the sky, you should be able to see it. It's going to resemble kind of an apple core look. You'll see the brightest portions of the nebula right here and over here. That's how it gets the apple core. This fainter stuff on the edges here will be a lot more difficult to see. So it's not something that you would really notice until you got to darker skies at this point. Now, one really cool thing about this nebula is it also has these wings out on the outer edges there. And I'm going to try it, see if we can actually do it. I know the camera won't be 100% focused with this filter in place. We're going to try to bring out those wings. So I'm going to switch filters. And we're going to go longer exposure. We have to do 60 seconds on this. I'm going to see if it's going to do this or not. So we're going to move the oxygen 3 filter into place. And this is a very narrow oxygen 3 filter. And what I mean by that, for those who aren't familiar with how narrowband filters work, narrowband filters only let a very select wavelength of light through to the camera sensor while blocking everything else. So, and when it does that, the amount of light that it passes increases the detail that you're going to see the closer you get to that exact wavelength that you want to observe. So a lot of these narrowband filters are actually measured in nanometers, very, very small measurements there. So generally an average filter is probably between 5 and 12 nanometers, which is narrow, but it's not super narrow. Then you get to 5 nanometer filters, which are getting very exact. The filter we're using right here is 3. This is the best filter you can get on the market. So that should be 03 right there, I'm thinking. We've been messing around with the filter wheel a little bit on this system, so I don't know if we're exactly on it. It might be the hydrogen filter. We have to look into it a little bit. I asked it to be 03. It says it's 03, but I think the filter wheel's kind of been messing with us recently. But we'll see. We'll let it stack. These are 1-minute images there, and we're going to try to bring out the wings of M27. Mike, we're using a Paramount MX Plus. So the Mighty from Software Bisque is the smallest of the bunch. Which is an excellent mount, killer mount. But we're using the next one up, the MX Plus, which holds 100 pounds. So that's what this is running. Both telescopes in the observatory right now are on MX Plus mounts. These systems right now are capable of doing 5-minute exposures without streaking, without any additional assistance or auto guiding. It's a very, very impressive setup. But that's what you want when you have a remote facility like this. So I'm going to try to pull some stuff out. This is very difficult to see right now, but we're trying to get the wings of M27. And when I mean wings, I mean like wings. You can start to see it right here. Here's one of the wings right here. You can see this gray outer area there. It literally looks like a butterfly. It's very pretty on this. And I don't think I have a great image of the wings recently, but it takes a lot of time to get those to come out, and they're very visible in the oxygen 3 band. So if you're doing astrophotography and you want to try to take a picture of M27, you've got a serious setup with some nice filters in there. Definitely try the oxygen 3 filter, let it sit there for a while, and try to get those extensions out on M27. You can really start to see it coming out now a little bit you are very faint. It takes a lot of work to get this to come out, but you can just start to see that coming out a little bit more. There is a lower portion as well, but it's a lot fainter than the upper wing is right here. But that's M27, the Dumbbell Nebula. Easy one to do from home. 4-inch telescope or bigger. And yeah, no, it's an easy one to do. In dark skies, it's beautiful. Very easy to see, lots of structure in there at that point. But it's a great object to go out and observe, especially if you're going to be getting a telescope for the holidays that are coming up. You know, like an 8-inch Dobsonian does a great job on this from the backyard. Maybe add a ultra high contrast filter or an oxygen 3 filter for visual work, and it's quite a fun object. There you go. You can really start to see the wing coming out a little bit more. So this must be the oxygen 3 filter. It's just been, that's a technical thing that's going on with our telescope right now, but I'm glad it's working. Looks good. That was a stretch. I didn't think we'd be able to get that in the image there, but that's pretty impressive. We've only been sitting on this for 4 minutes right now. So for 4 minutes, I don't think anybody's complaining at this point. So, but this is M27, the Dumbbell Nebula. Please go out and give it a shot, especially as the moon gets out of the way. We're kind of at the end of the season for it. I'm going to bring down the image stretch a little bit because we're going to switch objects here. Let me get out of this, and we're going to head over to the next target here. Now, like I said, it's been about a year since I've done this with the remote observatory, so I got to shake off some of the rust for this evening. But thanks for hanging out with me this evening. This is going to be a monthly thing. It'll get better as things move on. So our next target, I like to make, when I do these things, I actually like to do a wide variety of stuff. So we're going to do easy stuff tonight. We're going to do obscure stuff tonight. So we're going to move on to the next target, which is the Cocoon Nebula. And I also like to mix it up where we get a wide variety of types of objects. So we're not just looking at galaxies all the time or whatever. So we're going to send the telescope over here real quick. We found it. Go ahead and slew to the target. It's going to go over there and find it. So this is the Cocoon Nebula. This is up in the constellation of Cygnus the Swan. And while it's moving over there, I'm going to bring that up for you real quick. IC 5146. If you're not familiar with the IC catalog, that is the index catalog. It's a very large catalog of thousands of objects, but that's what we're digging in right now is IC 5146. So we're technically still in Cygnus. It is not far behind Deneb, but you are kind of close to the constellation of Lacerta at this point, as you can see right there. But this is where the Cocoon Nebula is. That's IC 5146, also known as Sharpless 125, which is SH2 125, which is right there. There's a bunch of, you'll notice when you're actually hunting these objects down, there's going to be a variety of different target catalogs that it's a part of. So this is my background. Don't worry about that. As cool as a shot as that is, let's bring that up. All right, telescopes on target. We're going to go ahead and go into Live Stack. And we're going to start off with the luminance filter again. I'm going to switch back to 30 seconds, and we're going to go ahead and start. It's got to switch the filters first. So we have 8 filters. What's interesting about the filter wheel that we have on there on this telescope is it's what's called a centerline filter wheel from FLI. It actually uses 2 carousels, and they rotate over each other. So one's got to move to get the filter where we need to go. It's this big balancing act. It's kind of an impressive system, but that's how we fit all those big filters in there. So it's taking the exposure right now. We're on IC 5146. This is the Cocoon Nebula. It's an emission and reflection nebula. An emission nebula is basically a star-forming region, mostly composed of hydrogen. So when we flip the hydrogen filter in a little bit, we'll be able to see it. But there's the Cocoon Nebula right there. That was a 30-second exposure, bin 2x2. The fact that you can actually get it is actually pretty impressive, especially with such a bright moon. But that's also the quality of the camera and the skies that are out there is very, very helpful. We are shooting up in the Milky Way arm So you can see right here, right now we were at M27 a minute ago, which is right down here. Now we're up here, but we're still in that Milky Way arm. So these areas are going to have really dense star fields. So lots of stars are going to be floating around in there. So that's why there's so many little points in this area. Now you might notice in the image here that there's also like this weird dark area around the cocoon. That's actually part of it. Not so much part of the cocoon itself, but it's part of another portion of that region. It's a dark nebula, and a dark nebula is a very dense dust cloud, which basically obscures the background stars from shining through. This particular one is part of the Barnard catalog. This is Barnard 168, and it actually extends well out of the frame here. We would need a much wider field instrument to actually see it. But these dark nebulas are very cool. They have a lot of very delicate structures in them, and they really just require lots of exposure time and dark skies to bring them out. And we're working in visual light right now. I don't have any of the narrowband filters in there. That was way too much on the stretch. Let's bring it back down. It'll get cleaned up as it moves on a little bit, but yeah, that was a little too much right there. So hopefully it'll correct itself here in a second. We're doing this all remotely. I'm in Arizona, telescope's in California, so there can be a little bit of delay. Sorry. But yeah, so let me get back to the Cocoon Nebula, IC 5146, an emission nebula, which is a star-forming region in the constellation of Cygnus. It also is a reflection nebula, and that's basically where you have dust reflecting the starlight of the nearby stars in the field. They're generally blue. These real faint little things are generally blue on the reflection nebula. We're actually going to check out a reflection nebula later at the last object of the night. This particular object is about 4,000 light years away from Earth, and it's about 16.5 light years in diameter. They say it's about 100,000. The central star formed about 100,000 years ago, this star right here. And that's what lights up that whole nebula. Now, this nebula is generally pink in color. If you actually look it up, it's pink because of the way the hydrogen in the clouds lights up. So that means that if we were to flip to the hydrogen alpha filter, there would be a lot of structure visible in there. So we're going to actually do that right now. You can see we've got some nice detail there from the exposures that we've been getting. This is a fairly difficult one to do because of how faint it can be. It's also quite a challenge visually. Visually, you'd probably want something like a hydrogen beta filter or a UHC filter under very dark skies to catch it. Probably about an 8-inch telescope would do it, but dark skies is ideal for this. But we're going to go ahead and stop this from exposing now. And I'm actually going to take the filters now and we're going to switch it. So we're going to tell the telescope to go from our visible light filter, which we're using right now, and we're going to switch over to that narrowband hydrogen filter. And hopefully you'll be able to see as the frames change here, the detail and the structure is going to be very different on what happens when we isolate that very particular wavelength of light. So going from a standard visual, all the colors essentially is what is all the frequencies are passing as we currently see here. Now we're going to switch to that specialty filter. We're going to isolate that wavelength that this nebula really emits a lot of light in. And it's going to pop up and we'll be able to see a lot of the structure and maybe some more detail that actually hides within the dark nebula there. So that's what's kind of cool when you start playing with these filters is you get to watch the different details. So hopefully that image will switch. It is going to be a bit darker because we're being way more selective at this point on how much light is passing. And so we're going to have to make up all the light that we just had exposed onto the sensor. But as that builds up, you're going to get some different structures that start to show up in the nebula, which is kind of neat. And the fact that we can do this with live streaming allows you to actually watch the differences change real quick, like you just saw there. Normally in astrophotography, this would be a lot longer process because we'd be sitting on this object for hours collecting data over and over and over again, building up that image. What we're doing here is kind of, imaging on the fly, real quick stuff. At this point, so you kind of just see what's there. This particular filter that we've got in place right here is the hydrogen alpha filter. Hydrogen beta for astrophotography really isn't used too much because the detail that you see in alpha and beta is the same. It just happens to be that the camera sensors are actually more sensitive in the red part of the spectrum, and alpha is a stronger wavelength than the beta is. So for astrophotography purposes, there's really no need to have a hydrogen alpha or hydrogen beta and a hydrogen beta filter in an imaging system, because you're basically photographing the same thing in different colors. Hydrogen beta is mostly in the bluish green, and then hydrogen alpha is in the red. So, and alpha is much stronger signal at that point. It's also less affected by the moon. Hydrogen beta, as well as oxygen 3, are in that blue part of the spectrum. And there's a lot of light pollution that shows up in those wavelengths. And there's also a lot of moonlight that can be visible in that particular frequency of light. So when you have a bright moon like we have out now, those types of wavelength, those filters can be more effective or more affected by the moonlight, where hydrogen alpha is way over in the red part of the spectrum and it's less affected. You can actually image in a full moon with H alpha and not really have any issues at all, because of it's a great filter to have if you're shooting from home, because it completely eliminates light pollution. There's not a lot of lights that we have out there. LEDs might be different, but a lot of the street lights and stuff like the sodium vapors and all that other fun stuff can actually be eliminated with an H alpha filter. So it's an awesome thing to have in the setup there if you want. So I'm going to try to see if we can bring some stuff out. I thought it would be a little bit brighter. There we go. There's some stuff coming out there. You can really start to see that structure. It almost looks like a heart. Not like a heart, but like a real heart. Where it's kind of got that elongated like lobe look to it. I'm going to get a drink here because we're going to be talking for a while. It's water. Don't worry about it. So that's actually looking pretty good. So this is about 3.5 minutes worth of exposure. We've got 7 frames stacked together there. 30-second exposures. Generally, when you're doing astrophotography, short exposures are okay, but generally you want to take longer exposures. So the way that works, while this is continuing to work on that, when you have a camera, an electronic camera, it's making a lot of electronical noise, like static. And all that, you're trying to get all those photons to hit the sensor there, but there's a certain level of static that's going on the chip naturally in your camera, all that noise and stuff. And you want to get enough photons to hit the sensor to where it actually starts to bring itself above that static, noisy limit. So the longer the exposure is, the more light that builds up on the sensor, the farther that builds up above the noise of the sensor. So that's why we try to stack images. You're trying to get that signal up above the garbage in the, not garbage, but basically the garbage in the image. So you want to make sure longer exposures are generally the best way to go to get the cleanest data. And that's what we're doing here. You can take shorter exposures, but you have to take a lot of them and then stack. Where, like we're doing here. But if we took a long, like 5-minute exposure, it would look phenomenal because it gets higher up there. Cameron, we're using a Skywatcher Esprit 150 tonight. It's running at native f7, no focal reducer. It is under a Bortle 2 Sky, and on the back it has a ZWO 6200 camera, so it's a full frame monochrome sensor. So it's quite a setup. It's a very nice system. And then we're using chroma filters. They're 50 millimeter square chromas. The 3 major filters I'm using tonight is the luminance filter, 5 nanometer hydrogen alpha, and 3 nanometer oxygen 3. So this is what we use for all of our pretty pictures and stuff like that for Skywatcher. It's a remote facility. out in Central California, Skies Away Remote Observatory. That's where it's hosted at. Maybe in the next couple episodes, maybe we'll have Brian, who runs Skies Away. Maybe we'll have him on talking what we're doing tonight. That's kind of the plan for these. It's going to be a monthly thing. And now that we have a better computer, better streaming system here that can handle the bandwidth required to run all this, we can hopefully have guests on as well, which would be kind of cool because it's talking for an hour and a half is a lot. So anyway, this is the Cocoon Nebula, IC 5146, in the constellation of Cygnus. You're probably looking at about an 8-inch telescope from a dark sky site, probably maybe a 6. But give it a try next time you're out. It is a summertime object, so we are getting to the end of the season of it, but if you get out to a dark sky site, it's a good one to try out. Visually or astrophotography, it's a nice one too. So I'm going to go ahead and stop that real quick, and we're going to move on to a much easier setup of objects. Let me get out of here real quick and move on to our next target, which many of you have probably seen. If you're new to the hobby, this is a perfect cluster to actually get out and check out. So Owen, the Skies Away Remote Observatory isn't open to the public for anything. It's a private property facility. It's made to host various remote telescopes from owners all over the world. You basically have to install, or have a team of people that you're involved with install the telescope there, and then you can run your telescope or equipment remotely from there. They're basically providing you the real estate for perfect dark skies, and then you pay a monthly fee to keep the equipment there, and they'll make sure everything's running, and then you just remote desktop into the telescope. That's what we're doing here. I've done these from my backyard before. My skies are, I live in Phoenix. My skies are trash. They're not bad, actually, and you can do a lot of good stuff with this electronically assisted astronomy like we're doing here, even in a light polluted location. But having this system remotely where I don't have to set it up and it's ready to go and it's all that, I use this almost every night for imaging purposes, so now we're just doing it for live stack. But if you want to know more about Skies Away, go to their website or just Google Skies Away Remote and it should come up. But yeah, you definitely want to have like an imaging team or, something like that. Okay, so we are on M15. M15 is the Great Pegasus Cluster. This was the first globular cluster I ever saw. The first time I ever saw this globular cluster was in the 24-inch Alvin Clark telescope at Lowell Observatory, and it was awesome. But this is a great target you can do from home. Like any size, you could see it in binoculars if you knew what you were looking at. I also want to go ahead and see if we can try this. I'm going to go ahead and actually up the exposures to a minute and see what we can bring out on this. So while that's doing its thing, we can talk a little bit. Let me show you where M15 is at. M15 is a very easy object to find. You can get it in a small refractor or a pair of binoculars from your backyard. In a dark sky, you can see it practically naked eye, is a little fuzzy. But it's right at the head of Pegasus. So you're going to find the box of Pegasus, go up the neck right here, and then the head. And it's right off the head of Pegasus, the bright star right there. And if I probably pronounced that wrong, but right off this bright star, it's very easy to find. Or you can just cheat and use a go-to telescope. That always works too. So, but that's where M15 is. It's an easy one to do. If you have a 6 or 8 inch telescope at home, it's a walk in the park. Easy thing to observe. And it's a very cool object. So what M15 is a globular cluster. It's a dense ball of stars. About 100,000 stars, I believe, are inside this. Maybe a little bit more. Depends on who you read. But globular clusters form a halo around the core of the Milky Way. And we have a couple hundred of them here in our own galaxy. M15 isn't any by any means the biggest, but there's M15 right there. This was a 60-second exposure. Actually looks pretty good. So M15 is located about 33,000 light years away, and it's about 175 light years in diameter. There are bigger clusters out there like M13 and Omega Centauri, which is in the southern hemisphere. We just barely get it in the lower part of the United States. But yeah, it's a challenging, that one's a little harder to get. But M15 is real easy to get. It's one of the stragglers, I guess, for lack of a better term. For the summer months, it comes up more in the autumn, where most of the globular clusters are visible in the summer months. But M15 is a great one to go out and observe. It's still visible right now. It was discovered in 1764 by Jean-Dominique Mardoli. I probably butchered. It's a French name. I'm sorry. And 1740. There's a typo there. 1764 is when he discovered it, but it was not cataloged until many years later by Charles Messier. So, you know, Charles Messier didn't discover all of these objects, but he did catalog a lot of them, giving us the Messier catalog. So this is the 15th entry. So we did M27 earlier, we did M15. We'll go through a couple more of them as the night progresses. They're very easy targets to go out and observe, even from, you know, an average backyard. So like I said, this is about 100,000 stars right here. It's one of the oldest known globular clusters in the Milky Way. It's about 1.3 billion years old. But yeah, it's just these dense globular clusters. They look like a pile of sugar on black tablecloth. It's really kind of cool to see. And when you get larger telescopes, you can actually resolve further down into the core. And what's interesting about M15 is it also contains, I can't pronounce it. David Majors brought this up already, but it contains Piece 1. I probably said it wrong, pronounced it wrong. Piece 1. It's the first planetary nebula to be discovered within a cluster. That was originally done in 1928. I have not, David, I have not seen it before. I should try it just to see what we could get out of it. I got to find out where it sits in the cluster because it's very small, and I don't know its angular resolution. It's probably a very small object. But yeah, this is M15. Easy cluster to see this time of year. Even with the moon up, you can find it in a very modest telescope. You don't need a lot of effort on something like this. Now, what's cool about something when you get out to darker skies and stuff like this is you can actually, let me try to zoom in here a little bit more. What I think is cool about a lot of these, well, there you go, real zoomed in. Maybe we can find piece 1 now. But I'm going to actually try that while we're talking. See if I can look up on Sky Safari here real quick where piece 1 actually sits in M15. I don't even know if it's going to show me, but why not? It does come up. It's 15th magnitude, so it's within some pretty serious... Okay, so it's just off the core. It's right... Piece 1, the little planetary nebula, is right around in here somewhere. That actually might be it. I wonder if we could experiment. So we're going to try this thanks to David here, digging up some interesting information. So right now we're doing visible light. This is our luminance filter. It's basically all the light there. Now, we know from studying planetary nebulas, and like I said earlier, that those type of nebulas actually emit light in certain parts of the spectrum. And one of those that they emit a lot of light in is that oxygen 3 filter. So what we're going to try, this is an experiment. I've never tried this before, but we're going to give it a go. we're going to move the oxygen 3 filter into place, and we're going to take an exposure of the area. Now, the cluster is going to probably look a bit different, but we're going to try and see if we can find where this planetary nebula is. This tiny, tiny planetary called Piece 1, which sits inside the cluster there. And let me see, object info. It's really, really small. So it's going to be, the telescope can easily get down to that faint of an object. So it's doable in the system, but we have to see if we can resolve it. Now this is, when you're trying to look for objects that are this small, like an arc second, which is very tiny angular resolution, you have to have very good seeing. And the site that the telescope's at can actually produce seeing of this caliber. We are using a 6-inch telescope, so we're going to really be pushing it here, but we're going to try and see what the O3 filter brings out and see if we can catch it. Of course, it's going to all look like dots, but you know, I don't know if I can even find a star map real quick while we're doing this. Let me see. Piece 1 M15 chart. See, this is what you really want to make sure. Oh boy. So here's what I found. It would be helpful if it was on the right screen. So when you're doing deep sky observing, like we're doing right now, and you want to hunt down some real stupid faint object, that's a highly technical term, stupid faint. You want to learn how to do star hopping. Star hopping is where you pull up a chart and you very, very carefully can analyze that chart on where it is. So we're going to look at this right here. And we basically want to match this area to that. And we're trying to point ourselves right there. And where's our chart? Up. Okay, let me see if I can figure out this thing. Kind of doing this on a whim too. So there's other fancier ways that we could get around this too. But it's right in here, I believe. So this one might have to wait. I don't want to keep you guys waiting on this, but never tried this one before. Kind of interesting. I'll go ahead and shoot this later and see if we can come up with a better chart. Normally I try to plan this ahead of time so I can actually see this stuff, but it's in there somewhere. Piece 1, real tiny planetary. We'll try that in the future on another episode of this. I'll try to do some pre-planning there. But this is M15, 100,000 stars, globular cluster in the constellation of Pegasus, about 33,000 light years away from the Earth, 175 light years in diameter. Definitely go out, give it a shot. It's a great one to do from the backyard with your family. And yeah, give it a go. Now this next one, this time of year, is probably one of the easiest targets to find. And that's Andromeda. The Andromeda galaxy, M31, is just a staple this time of year. Much like Orion or M42 is in the wintertime, Andromeda is really the target of autumn, at least here in the northern hemisphere. And everyone observes it. And that's because it's the brightest galaxy that we can see. And you could actually get a very nice view of this in a small pair of binoculars from a very dark sky. And it is up right now. It's practically overhead if you were to go out right now. There it is right there, at least on Stellarium. And but you can see this naked eye. One of the best views I've ever seen of this is in 70mm binoculars from a dark sky. You don't realize how big Andromeda actually is until you actually get out to a dark sky site and really see it. So it's quite a sight. I mean, obviously the bigger the telescope, aperture is always helpful, but this telescope actually does a very nice job on it. And we're going to let it go right now. We're going to switch the luminance filter back in. heck, we'll just keep it at 60 seconds and let the camera just run wild. It's actually big enough to where it will not fit completely in the field of view of the telescope. It just barely squeezes the majority of it in there, but it will extend outward from the field of view of the telescope here. So I'm going to drink real quick. There we go. So we're doing a 60-second exposure. It's a bit overkill for something like this, but it makes it look better at the end of the image there. But while we're doing that, Andromeda, or M31, is the furthest object that you can see with your unaided eye, about 2.5 million light years away. From a dark sky site, you could see it. From your backyard, you'll probably need like a small set of binoculars. It's going to look like a little fuzzy. And then from darker skies with larger telescopes, you'll be able to start to get the dust lanes and all kinds of cool detail in there. But it's 2.5 million light years away from the Earth and 220,000 light years in diameter. The earliest known record of Andromeda is from 964 BC by Persian astronomers, where they described it as a little cloud. There we go. That's a 60-second exposure. Not too bad with a just after first quarter moon shot. So you can see all the dust lanes in there. That's pretty darn good, I would say. That's cooking with gas at that point. Now, the first telescopic observation of M31 was actually done in 1612 by Simon Marius. Many other observations and discoveries of M31 occurred throughout the 1700s, but it wasn't until Charles Messier actually cataloged it in 1764 when it officially became M31, the 31st entry into his catalog. Now, on top of that, William Herschel observed this galaxy in 1785, and that's where he finally made it the Great Andromeda Nebula. At the time, we had no idea it was a galaxy. They just called it a nebula, which was inaccurate, actually. But we didn't know. We didn't have any observations to tell us that at that point. The first image, actually, of Andromeda was not captured until 1887 by an English astronomer by the name of Isaac Roberts. That's where he was able to show the spiral structure that we're seeing here. You can actually see that spiral, all those dust bands and arms. He was able to capture that in his glass frame images there, and that was kind of interesting. So, but that was 1887. Now, several years later, in 1912, we had Vesto Slipher, who, from Lowell Observatory, Lowell, observed the spectrum of the Andromeda Galaxy and was able to measure the velocity of it. And at that time, it was the highest velocity ever measured at 300 kilometers per second. So they were kind of getting some interesting readings from this that maybe it wasn't a nebula, maybe it was something else. So then in the 1920s, this big debate started called the Great Debate on whether M31 was actually a nebula or a galaxy. And it went back and forth between well-known astronomers until 1925 came around and Edwin Hubble showed up and was able to do some observations that actually proved that M31 was much farther away than we actually thought it was. This kind of established the fact that it was not actually a nebula, but it was actually a galaxy. So that's when things really hit the fan at that point. M31 formed about 10 billion years ago, and it contains about 1 trillion stars, about 460 globular clusters, and 2 satellite galaxies, which we can actually see in the frame here. So we have M31 right here, we have M32, the little companion, and we have M110 down here. These are easy to see in about a 6-inch telescope from even average skies. You can go out in your backyard when there's no moon, and you could probably catch some little glimpse, particularly of M32. M32 is really easy to do. This looks like a little bright fuzzball, highly technical term. And then M110 is a little bit more faint and obscure to see, so slightly darker skies would be better to see M32 or M110. I'm sorry, at that point. But it's an awesome. It's one of those that never gets old. So it's you just have to observe it in every telescope you can. Now, we've actually found that the Milky Way and Andromeda are coming at each other about 100 kilometers per second. And we're basically expected to hit with each other in about 2.5 billion years. But there's so much space between the stars and these galaxies that it's very unlikely that any of the stars will actually hit each other. But due to the gravity that all of this contains between the two galaxies, a lot of stars are going to go flying. But thank goodness, this is 2.5 billion years away, and none of us will really have to worry about that at that point. So, yeah, don't worry about it. So this is M31 invisible light. It does have some star-forming regions in it, which is kind of cool. I don't know if I want to try it with this because they're not as bright as they could be. They take longer exposures. We are going to try this experiment in a minute on another galaxy. But yeah, that's pretty impressive. This is 5 minutes right here from Falling Eagle, this observatory we're working at. It does a very nice job. But we're not done with Andromeda. And Mike beat me to it. He's like ahead of it. He didn't even see my notes, and he always knows where we're going with it. But what's really neat about Andromeda is the globular clusters that you can see in and around Andromeda. So I'm going to go ahead and shut this off right here. And we're going to go find one of those globular clusters that are in Andromeda. It's actually a lot easier than it probably sounds. But it's one of those things where you can always impress your friends with it. Especially those that are usually observing some of the brighter stuff. So we're going to go, it's not far. It should bounce right over there. There we go. Go back to this. I tried this earlier, so I know it works. We don't need to expose that long. But now we're going to actually try and get a picture of one of the brightest globular clusters in the sky there and see what we can see. I like to go after really weird, oddball stuff just because there's so many cool things to see. The Messier catalog is great. You know, Andromeda's great. Pleiades is great. All that stuff, that's like the greatest hits of astronomy. You have to like it. But there's a lot of really cool, obscure stuff. Don't be afraid when you're doing this stuff, whether you're imaging or observing, to dig out a book or look in Sky Safari or dig up something on the internet. Don't be afraid to go after something that's just off the wall. Because there's so many cool things out here. Like this, which I'm sure some of you are staring at this being like, what the heck is this? Now, this target that we're on is a part of the Andromeda galaxy, but it's extremely small. So that is where we're going to have to be able to zoom in. I like to think of this as a very miniature version of M13. If you've ever observed M13 before, it sits between two bright stars. And then the cluster is right above there, kind of forming a 90-degree triangle. This is exactly the same on a much, much, much farther scale. So if we look right here in the center, right there, our little triangle, these two little guys down here are stars. The little fuzzy up at the top there that looks a little bit bigger is a globular cluster. The globular cluster is called Male 2 or G1. Pick your poison. Just that's what it's called. This is the easiest globular cluster to find from Andromeda, and it's actually quite a distance away. It's about 130,000 light years away from the core of the Milky Way, and it's not even in the arms of the Milky Way. I'm sorry, Andromeda. So it's a bit of a distance. You can see this in a telescope, like an 11-inch, 10, 11-inch telescope with some good magnification, some good seeing actually will help. But about a 10-inch telescope, you can grab this and impress your friends with it because it is way off the deep end for something like this. So You know what? I want to try one thing. So we're binning 2x2 right now. That's generally how we get real nice sharp images. We're going to open this thing up to its full resolution. All 61 megapixels firing at once. We're going to try to get this as sharp as possible and really maximize the seeing conditions out there at the observatory tonight and see if we can kind of resolve it a little bit further. So I'm going to never tried it before. Why not? We're all together hanging out tonight. Let's try it out. So this globular cluster is about 2.5 to 3 million light years away. It shines at about magnitude 13.8, 14th magnitude, which means, yeah, 10-inch telescope, and it is small, so you're going to have to be able to go after it with some magnification. This was first discovered in 1953 by astronomers Nicholas Mayall and Olin Egan. When they were actually looking at glass plates that were captured by the Palomar 48-inch telescope in 1948. So they had to actually bring up an old plate and look at it. And while they were observing, or while they were actually looking through all these plates, they were able to see it, that it looked like something a little bit different. So now we have the telescope camera running at its full 61 megapixel resolution. And it looks a little better, but, you know, it's tiny. So, need a bigger telescope. But it's doing pretty good. You can see, we did resolve it. You can actually break the triangle up a little bit more. So, the seeing's pretty good out there at this point. For my imaging friends who are watching, we're doing about 0.7 arc seconds per pixel right now on the telescope. Not bad for a 6-inch refractor. But that's what it is. All about matching your pixels to the focal length of the telescope, and your seeing will get you the maximum resolution that you want to do. But yeah, so kind of cool for that. But yeah, this is the brightest globular in the Andromeda galaxy, called Mayall 2, or G1, located about 130,000 light years from the core of M31, its main galaxy. And it's a fun one to actually go out and observe. So it's about 443 light years in diameter, so it's a huge globular cluster, which is why we're actually able to see it. They actually believe, from observations here, that it's the leftover core of a galaxy that once used to be not so much a globular, but, you know, that's what they've been able to observe with that. So that's Mayall 2, G1. That's a very cool one to go after. Highly recommend it. And it's just a great one for off the beaten path kind of things. I'll have to try it when the 28-inch telescope is done. Give that a go. So, but that is Mayall. Should try, if you're into imaging, you should give it a go. It's something you can do from your backyard. It's not a very difficult thing with the cameras. It's just tiny. That's the only challenge it is. So if you're looking for pretty pictures, it could be difficult. All right, we're gonna go. Did I bounce over something here? Let's see. Where's that? Oh, okay. No, we're still good. Just making sure I'm not bouncing all over my notes. All right. We're going to go to another one. And this is another cool object that's very easy to find because it's right next to a big bright star called Mirach. Let me pull this up real quick while it's slewing over to that target. So NGC 404 is what the galaxy is called. And it's actually right next door to M31, just down the chain of stars, next to the bright star Mirach. Now, Mirach is a naked eye star. You could walk out into your backyard, look up, and you would see it. It is that bright. But right next to Mirach is a very small little fuzzy. And it's a galaxy, actually. And it's called Mirach's Ghost, or NGC 404. I really like objects that have that real bright, contrasting, bright star. Real bright star, real faint, obscure thing next to it. I think that's really kind of cool. So we're going to go ahead and shoot this target. It's called NGC 404, or Mirach's Ghost. It shines at magnitude 10, so it actually is doable in an 8-inch telescope. It looks really good from a dark sky sight because it just pops so much better, especially in a very large aperture telescopes. It's about 10 million light years away, and about 10,000 light years in diameter. It was originally discovered by William Herschel in 1784, and it's easy to find because it's right next to Mirach. So give that a try when there you go. It actually looks like a reflection. And a lot of people would probably, if you're not familiar with it and you're kind of glancing over the area and you're not paying attention, you'll probably find that you're going to think it's a reflection, but it's not. It's actually a galaxy that's about 9 million light years behind the star. So definitely give this one a shot. It's on the star charts. It's easy to find, especially because it's right next to a naked eye star. But it's a little distant galaxy. And this particular galaxy is a dwarf lenticular galaxy. That's the type of galaxy it is, which means it's a mix between an elliptical galaxy, which is usually just kind of a jumbled mess, and a spiral galaxy. They generally have a large disk, but they have very small arms, which you can see it's kind of disc shape. You could probably get a better image of it somewhere as I zoom in a little bit more. Let this kind of snap in. But it's kind of diffuse. But you have that big bright star Mirach right there. And then the galaxy right there in the center of the frame. That's NGC 404, Mirach's ghost. That's 10 million light years away from the Earth. Mirach, the bright star that we're seeing right there, is only 197 light years away from the Earth. So it's very close. So that galaxy is quite far in the background there. But very cool object to see. It's kind of cool because it's got that contrasting bright star in there. But it's a fun one to go out and check out. Highly recommend it, especially if you're in a dark sky site and you're looking for something a little bit different. Bust that 6-inch or bigger telescope on there and you'll be able to find it. You could probably even do it in a 4-inch telescope, mind you, but it's a fun target to check out there. It's not the most impressive detail-wise. There's not a lot going on for it, but it's still very neat to be able to see that galaxy sitting next to a bright star right there. So give it a go. NGC 404, Mirach's ghost, and try it from your backyard. If you don't get it, it's too bright, no big deal, but at least you tried it. Okay, well, we didn't sit on that one that long. It's kind of just a cool one there. But the next set of objects we're going to be going into a little bit more detail on because there's more to talk about on them. And we're not too far from our next set of galaxies. Okay. I'm officially out of water. We're going to have to make this the stretch home. All right, so the telescope's slewing over to our next set of objects. This is a very cool collection of objects. There it is. It's moving over to our target. Should be on it now. So we're going to flip this in. And we'll stick with 30 seconds. That's fine. It's working. All right, so this next set of objects, kind of going a little bit further into that oddball set of stuff, is Stephan's quintet. Stephan's quintet is a galaxy group in the constellation of Pegasus. It ranges in magnitude between 14 and 16.7, which means it's kind of in that 12-inch category and bigger. It looks great in an 18-inch or a 15-inch telescope. It looks very nice in something like that. Might need some magnification to it to break up the different galaxy companions. But this was originally discovered by Eduardo Stephan in 1877 in Marseille, France. It's not far from a much brighter galaxy, which you can see. It's actually a galaxy group, but there's a bunch of stuff that we're going to be talking about right now. I'm actually going to zoom this in a little bit so we can kind of get everybody, the whole family tree in here while it's taking some pictures for us. Okay. All right, there's Stephan's quintet. And let me try to get the other galaxy down in here. All right, there we go. So I've really got it kind of squeezed in here, but Stephan's quintet is this galaxy group at the top right. You can start to see a lot of the detail comes out. Down here is the Deerlit galaxy, NGC 7331, and some of its Deerlit companions. So there's a lot going on in this particular area. So Stephan's quintet, which is up at the top right here, I'm actually going to try to brighten this up a little bit. See if we can bring some of this out a little bit. There we go. Got some nice detail in the spiral arms of NGC 7331 down here. These are 30-second exposures that we're doing. All right. Stephan's quintet up at the top right there that you can see. Originally discovered by Eduardo Stephan in 1877 in France. This was the first compact galaxy group ever discovered. There's actually 5 galaxies observed in the cluster. However, there are only 4 of them are actually physically associated with each other. NGC 7320, which is this one right here, this larger bright one, is actually a foreground galaxy compared to a background galaxy. So NGC 7320, which is this one, right up here, if you can see my cursor there, that one sits relatively close, about 39 million light years, 40 million light years away from Earth. However, the rest of them, and there's a bunch of them packed up in here right in here, those sit between 210 million light years and 340 million light years away. Quite a jump. So you actually have 5 galaxies when you look at this in a telescope. There's 5 galaxies, but 4 of them are only part of the actual cluster. And they're actually able to observe that by studying the spectrum of these galaxies and reading off the velocities of them. They can actually tell, the redshift of how they're moving and see which one's moving faster, which one's moving slower, and how that is relative to us. So that is Stephan's quintet right there. And we'll try to zoom. Let me just, while we're on it, we're going to break this into 2 things real quick. Let me just drag Stephan's quintet back in here. Go into some detail. This is a very cool object to see from dark skies, especially if you've got a 12-inch telescope or bigger. You can really break the cluster apart. I saw it in a 17.5-inch once. It was a very nice view. And then if you get a chance to put a real big telescope on it, it just gets more impressive. So let me try to get this centered where we want it. There we go. Let me blow this up. Well, too much. Too much. Back that off. Maybe one more. All right. Stephan's quintet, this little galaxy cluster. The one on the right here, like I said earlier, that is NGC 7320. That is the closest galaxy to us, 39 million light years away. It's not actually physically part of the cluster. It's just optically part of the cluster. It's actually a foreground galaxy, where the rest of Stephan's quintet is a background collection of galaxies. So everything right in here is actually part of that true cluster, about 210 million to 340 million light years away from the Earth. But that is a galaxy group that a lot of amateurs could actually get. You probably need some decent skies for something like this, but photographically you could do it from town. It's not too difficult. But that is Stephan's quintet. If you're looking to get started in galaxy clusters, this would be the one to start with. It's one of the easiest ones to see. But that is a great set of objects. Now, right next door, and a very easy one to find actually, is the Deerlit galaxy group. And the brightest one in there, called the Deerlit galaxy, I'll let you look that up on why it's called that way, is NGC 7331. And NGC 7331 is kind of a cool galaxy because it's got a lot of nice detail that you can see in the arms there. Lots of structure in the image there. This is about 40 million light years away. It was originally discovered by William Herschel in 1784. Now, this galaxy actually shares a lot of similarities with our own Milky Way. So a lot of people have dubbed this the Milky Way 2. But what's interesting about the Deerlit galaxy, NGC 7331, is the central core of the galaxy is actually rotating the opposite way from the disk. So everything in the center here is spinning one way, and the rest of the disk of the galaxy is spinning the other way. So kind of an interesting galaxy right there. This galaxy is easy to see from even basic dark sky sites. Like a 6 or 8 inch telescope would have no problem getting it. If you're in a very dark sky and you've got a telescope of that size, you can start to see the structure and the galaxy there. And then obviously larger aperture is really going to back you up even further. So it's kind of a cool one to see. And then if you know where this one's at, just up above it, just up to the edge there, you can try to get Stephan's quintet. So if you want to try and find Stephan's quintet, the best way to do that without a go-to system is to locate NGC 7331 and then go up a little bit and try to find it there. But that's the easiest way to do it, because this is a very easy galaxy to find. Get some extra little companions out there, and then you can make the jump into deeper waters with Stephan's quintet. But yep, that is the Deerlit group and Stephan's quintet right there. So very nice little set to go off of, and kind of a cool thing to see out there. So nice galaxy group, and usually a lot of these they're out there. You just got to look for them. Okay, we're going to move on to another well-known galaxy that's right up in here in this area. And that is M33, the Triangulum galaxy. This particular telescope setup frames this so remarkably well. It's very impressive how well this matches up with this particular setup. I do want to go a little bit longer. We're going to pump it up to 1 minute. Because M33, unlike M31, the Andromeda galaxy, has a lot of nice structure in the arms. It's very easy to see a lot of those dust bands in there, where M33 gets a lot more granular and diffuse as it heads away from the core. So longer exposures are going to help you bring out some of that, and darker skies apparently are also helpful there. But this is the Triangulum galaxy, M33. It's about a little over 3.5 million light years away from the Earth, and about 60,000 light years in diameter. It's the third largest galaxy in the local group. That is the Andromeda galaxy, us, the Milky Way, and then M33. So that we've taken a look at all that over there. So this was originally discovered by Giovanni Battista in 1654, but it wasn't there's a bunch of stuff going on in here too. Satellites. There's all kinds of satellites going off in this area. So wonder if prime reason of Starlink stuff right there. You can see just all those streaks. Actually, that might have been, I don't know why it did that, but anyway, we're going to let it do its thing. That's M33 though. Don't mind the streaks. No big deal. We're just having fun. M33, like I said, was discovered in 1654, but it wasn't categorized by Charles Messier as the 33rd entry into his catalog until 1764. Herschel cataloged this object in 1784, but he also cataloged some of the H2 or star-forming regions that are in the arms. We're going to take a look at those here in a little bit as well. So, as you can see with M33, it's a lot more diffuse. As Mike said in the chat, the brightness of the surface brightness of this is a lot fainter than Andromeda. So when you're trying to observe this galaxy, it's going to look more fuzzy. It's not going to look as detailed as Andromeda. Andromeda is a walk in the park, very easy to see, lots of nice structure on a modest telescope. M33 takes a little bit more punch to bring out. So, and you can see some of the structure in that, and the image right there. It looks rather nice. but it doesn't have that pop that Andromeda does. So this requires more exposure time, and it also requires darker skies to be able to see it. You can actually glimpse this naked eye in the darkest of skies. A pair of binoculars would do a very nice job on it from moderate skies. But when you get a telescope on it, especially a large telescope, you can actually really dig into that even further. Now, when you're doing astrophotography of this, you can do it in town. It does do well with a one-shot color camera. Monochrome does a nice job on it. But one thing I would like to mention is that if you are going to be doing that, I'm going to go ahead and stop this real quick. Especially if you have a narrowband set of filters, I would always recommend going through and doing hydrogen alpha on top of your color data when you're shooting this galaxy. Reason being is it has a lot of star forming regions. H2 is what those are called, H2 regions, which are emission nebulas. Those are star forming regions, and they're very abundant in the hydrogen alpha wavelength. So what we're going to do here, this is visible light that we see right here. It looks good. You can see a lot of cool structures. You can see some of those star forming regions like NGC 604, which is right up here. That's the largest star forming region in this galaxy. It's kind of like the Orion Nebula is for us in the Milky Way. It's about 1,500 light years in diameter as well. So it's a big old chunk of some. I think it's 1,500 light years from the core. I'll have to go back and check. It's big. But what I'm doing right now is we're actually taking a 2-minute exposure while we're talking in hydrogen alpha. So what you're going to be able to see is we're going to watch this switch in a minute, about a minute, from literally a minute. We're going to go from the visible light that you're seeing right now on the screen from the past couple images that we took, and it's going to switch that to the narrowband hydrogen arrangement. And you're going to be able to see a lot of those star-forming regions that are actually hiding in the arms. And my cursor right here is actually on the largest one, NGC 604. But there's another set of them, NGC 588, NGC 592, NGC 595. And anybody who might be wondering what NGC actually means, that'd be New General Catalog. It's like almost a master catalog that encompassed Messier as well as all these other catalog objects as well. So it's about to switch here. We're going to watch this real quick as it jumps from visible light to hydrogen. And we should be able to see all those star forming regions pop right out as most of the detail from the galaxy goes away. There we go. You can still see, let me try to drag this up a little bit. And it'll look better as more images, but you can start to see all that major, all that other part of the galaxy disappeared. But you can see all these little regions in here. So there's 604 right up there. That big H2 region that was major star forming region is in there. And you can see all these other little bits in there. So there's a lot of star forming going on inside of M33. So the hydrogen alpha filter is actually able to let us see that a little bit more. So it's kind of a neat thing to see right there. But that is that is M33 and its various star forming regions. And yeah, that's pretty much it. We're actually chewing through this real quick. We've already blown through an hour and a half. That's crazy. We've got 2 objects left for the night. Thanks for hanging in there with us. This is the first time we've done this in like a year. So thanks for joining us. I am going to get a December date put together here soon. So I've got a lot of cool stuff coming up in December. You know, a constellation of Orion is coming up. That gives us the Horsehead. That gives us the Orion Nebula, M78, the Witch Head, all kinds of crazy stuff out there. So definitely join us next month as well. Maybe we'll start having special guests on too. We're going to try to make this more elaborate and fun. But thanks for all of you who've been hanging out with me this evening. So we're going to head over to the Bubble Nebula. And because we already have the hydrogen alpha filter in place, when it wants to listen to me, there we go, Bubble. Slew over. This is one of my favorite objects in the nighttime sky. It's actually a lot smaller than people think too. You see a lot of images of the Bubble Nebula sprawled over the internet. A lot of good stuff out there, but it's actually very small. So longer focal length, bigger optics tend to help, or just zoom in on it. But you'll see just how small it is. So we're gonna switch this over. Let's do some 1 minute exposures here. There we go. Start. All right, so the Bubble Nebula NGC 7635. Let me bring that up on my star charts here. NGC 7635. So the Bubble Nebula is actually in the constellation of Cassiopeia, right on the edge of Cassiopeia and Cepheus. So you'd have to find Sidar and Cath, and it basically points you right to where the bubble is going to be. Or again, you could just use your go-to telescope, because the bubble is very difficult to see, almost impossible from light-polluted skies visually, but via cameras and some narrowband filters, you can actually start to bring it out. So we're doing, especially with an H-alpha filter, very helpful with the hydrogen alpha filters to cut out the light pollution. About 11,000 light years away from the Earth, about 10 light years in diameter. The bubble was originally discovered in 1787 by William Herschel. He noted, there it is right there. Looks pretty good, actually. And for reference, right down here, there's a cluster. That is M52, Messier 52. It's an open cluster, which is right next door to the bubble. Makes it very, very easy to see right there. And let me try to bring this up a little bit as it takes another shot there. But you can see the bubble right there. And I'll also try to zoom in here. It looks pretty neat, actually. So there we go. There's the bubble. Easy thing to do when you're doing this live stack stuff. It's a lot of fun to be able to show people. And you can do this from in town. Yeah, we've got a nice setup at the observatory, but you can do this from in town. It's not a big deal. But anyway, Bubble Nebula, nearly impossible to see from a light polluted location. But with the cameras and a light hydrogen alpha filter, it is no problem at all. So, Bubble Nebula, 11,000 light years away, 10 light years in diameter. The bubble is actually created by strong stellar winds from the hot central star. That star is SAO 20575, which is this star right here in the center there. That has stellar winds that are pushing the dust out, making this bubble. And that star is actually pretty big. It's about 10 to 20 solar masses. And what that means is one solar mass is basically equivalent to our sun. So it's 10 to 20 masses in comparison, so it's a lot bigger star. So it has a lot more capability with that stellar wind right there, being that it's very high temperature, and it's got more capability to push that stellar wind off. And that is what basically is illuminating and creating the bubble right there. Now, if you're actually going to go out and try to observe this from a dark sky site, I would say you probably need about a 10 to a 12-inch telescope for starters. I've done it in a 14-inch Cassegrain, and longer focal length actually tends to help more because of how small the bubble actually is. And the easiest thing to find is this bright section right here. So you see this part right by the star and kind of the brightest curve of the bubble. That is the easiest part to see. And the way I find that's easy to observe it is when you're actually on the target, take your hand controller, make sure it's on a slow slew setting, or if you have a Dobsonian, grab the scope and slowly move it back and forth and watch what moves with the field. And that'll give you a real good frame of reference of what's actually there and part of the structure there. But the bubble is doable. Gonna bring this up a little bit more. This is in hydrogen, so we're really pulling a lot of detail out. But you can do this from home. An H-alpha filter on an imaging setup. Easy to do from the backyard. But it is a smaller target than a lot of people think it is. If you're in a dark sky site, go ahead and give that a shot. Try it without a filter if you're observing with it with your eye and a telescope. And if not, try a UHC filter. That would probably help. Or oxygen 3. Oxygen 3 will help as well. But the bubble's a very cool object to go out and observe when you can. So hopefully you enjoy that. And that is NGC 7635. If you want to go out there and try to find it, or the bubble. All right. So that is pretty much it for the evening. I've got one target left. I've saved one of the biggest ones for last, especially right now. It's an easy one, but everyone will enjoy it, and that is the Pleiades star cluster. It barely fits on the telescope. Probably should tell it to move over there, shouldn't we? Not just find it. Slew. So this will be the last object for tonight. The Pleiades star cluster is something that is easy to see. You can go out, if you just live in a common neighborhood, go out, look towards the east, and you should be able to see it naked eye. Or a pair of binoculars would be easy to see from your driveway. Small telescopes do a great job, and if you actually get out to darker skies, it's a beautiful cluster to see because there's just so many stars. So we're going to go ahead, do a 60-second exposure on this. This will be my last object of the night. Wraps up about an hour and a half program right there. Thank you for everyone who's hung out with me tonight. Appreciate you all being here and keeping the chat going. We'll be doing this again next month. I'll find a date for that. Maybe pick one where there's less moon so we can go after some more faint objects there. But this one's the last one, M45, the Pleiades cluster. It's an open cluster in the constellation of Taurus the Bull, about 500 light years away, about 15 light years in diameter. Very easy object to see, naked eye from in town. This object has been known since the age of antiquity. That'd be about 8th century BC to 6th century AD, a while, essentially. First referenced by Homer in the Iliad and Odyssey in 1750 BC. And it's also been referenced 3 times in the Bible, as well as other texts such as Hindu and the Hindu and Islamic faiths. It is also mentioned in their writings as well. It does look like a little dipper. I like to call it the micro dipper personally, but there is a lot of people who get it confused with the little dipper because it does look like a tiny dipper. And what's cool about this is there's also a nebula floating around in there as well. This is also known as the Daughters of Atlas in Greek mythology, and you have the 7 bright stars that represent the Daughters of Atlas, and then the 8th and 9th star are Atlas and his wife. So, and it was originally cataloged by Charles Messier in 1769. Now, what is interesting about this is, so there's the Pleiades cluster, the open cluster of stars that you can see there, and it sits in this dusty region, and this is called the Mirach Nebula, NGC 1435. Now, what's interesting about this is observations have been made from the star cluster and the nebula. And what's been found is the nebula actually has nothing to do with the Pleiades at all. The Pleiades cluster is actually passing through a dust region. It just happens to be in our time of existence here that we get to see the Pleiades lined up with the Mirach Nebula, which is that dusty reflection nebula that you see there. That's basically just particles of dust floating out in space, and the starlight is being reflected off of that. That's a reflection nebula. Now, when you're trying, this is very difficult to see. You would need the darkest of skies to really be able to see this nebula because it's very faint and delicate. For the cameras, it's easy. Cameras are much more sensitive than the human eye, but even in town, this nebula can be difficult to get because there's no filter that can really make this work. You really need this to just be good skies. Reflection nebulas do not benefit from anything, light pollution filters, narrowband filter, nothing. You just have to go for the good skies. You can do it from home, especially with these modern day cameras. Give it a go. See what happens. But yeah, this is the Pleiades nebula. I'm sorry, cluster M45. You may also know it in more modern day society as the Subaru logo, because that's exactly what that is. If you drive a Subaru, that is the logo on the car, is the Pleiades cluster. But there's several stars, and there's actually 500 stars total in the open cluster. I'm going to try to zoom in on some of the nebulosity that's in here so you guys can check it out. But there's some really cool, nice things in here. It actually looks a lot like paint strokes. They're very delicate, intricate nebulosity there in the Mirach Nebula. But it's definitely a cool one to go see as we kind of tour through the cluster there. All of this is blue. Very pretty blue detail there. So it's a very nice object to go ahead and take a look at there. I'm going to check something real quick. Okay, everything's good. But yeah, that is the Pleiades star cluster M45 up in Taurus the Bull. An easy one to go see right now. It's one of the nicest objects, in my opinion, in the nighttime sky, just because of how much detail in there. Let me see if I can pull up a finished image real quick. I actually have a finished image of this object just to kind of wrap up the evening here, so you can kind of get an actual look at what it should look like. But this is through this telescope and the telescope next to it. But this is a colorized version of the Pleiades, as you can see there. So colorized shot, raw shot. So there you go. Same orientation and everything. The way I generally do this is, you saw there were two telescopes in the observatory. Telescope we're using right now, I would have shoot the luminance, which is what we're doing here. It's all the structure. And I have the other telescope that has a color camera equivalent. Take color, and then I apply them on top of each other, and it gets the finalized image there after several hours of exposure as well. So that is a finalized shot of the Pleiades right there off of the scope. And then the raw shots that we're seeing there. But yeah, that is pretty much it. Thanks for hanging out tonight. I hope you have a great weekend, and it's been a lot of fun with you guys here. Thanks for putting up with me for the first time being back doing this. Each time's going to get a little bit better. Next month, we'll hopefully have a special guest on. Maybe we'll drag Brian from Falling Eagle out, or somebody else. I'll find somebody who wants to put up with us for an hour and a half. But keep an eye on social media. Big thanks to Skywatch for letting me sending out the email blast and supporting this. And yeah, thanks very much, everyone. I hope you have a great weekend. Thanks for hanging out with me tonight, and we will see you guys next month. Take care, everyone. Good night.